Okay, hello everybody. Welcome back to Conceptual Physics today. Hopefully you had a great weekend. So this is our last PowerPoint for the chapter. I will have another video later to do some math, but this is our last PowerPoint. Okay, so the first note today is about the projectiles. So remember about projectiles, right? Because they're the things that are only influenced, or they're only being forced on by gravity and maybe some air friction. But a projectile then, so here's our first note. A projectile launched horizontally. You guys remember what horizontally means, right? And straight across. At 30 meters per second, will travel 30 meters in 1 second. So do you agree with that? Okay, so just to make sure that you know what I'm talking about, in the olden days, they had these things called cannons, and they still have them. They're just, I think, mostly on tanks now instead. So if you launch this ball here at 30 meters per second, that means that in 1 second, it's going to be 30 meters downrange. So that's a word, downrange. Okay, so that'd take 1 second to go 30 meters. Now, it looks like I drew it less than horizontal. Do you agree with that? Like it's down from where it started. Why? Very good, Zocker. Yeah, it's because gravity is always on a projectile, and gravity is always forcing things towards the center of the earth. So gravity is forcing things down. Now, what's going to happen in the next second? So if it went 30 meters per second in the first second, what do you think happens in the second second? How far does it go? Very good. Thank you very much, Zocker. Exactly. Another 30 meters. So in the next second, it's going to be another 30 meters downrange, right? Now, that's 30 meters downrange, but what are you noticing besides that? So, you start out here, the ball starts out here, and it ends up here after the first second. But the second second, it's gone even further. Can you tell me why that is? Why is it falling further in the second so good? Yes, that's exactly right. Because the velocity in the y direction is getting bigger. So, right here, there's no velocity in the y direction. There's just x velocity. But the moment that it's a projectile, it starts gaining y velocity. So we'll just say that at this point, this has moved down to here because the y velocity is there. But here, Zocker said, well, because of the force of gravity, it's accelerating, and the y velocity is bigger than it was the first second. And if there's a bigger velocity in the y direction, there's going to be a bigger displacement. And yeah, we've been saying that a lot, but not everybody has been recognizing that. So there's another chance for you to understand that. Okay, so if you look at this next note here, it says increasing or decreasing the horizontal velocity will not change the hang time of a projectile, because the horizontal and vertical velocity are independent of each other. Just to reiterate, we saw that, hey, this y velocity is changing, but this x velocity is not changing at all because these things are independent. It's kind of hard to believe because when you see a ball move, you see the x and the y working together on the ball. So you have to remember that the x velocity is constant throughout the whole projectile motion, but the y velocity is constantly changing. Okay, just to kind of remind you of last week's lesson, the whole idea of the long jump here has everything to do with both the horizontal and vertical. But just to remind you, so if I'm jumping off the board for a long jump, I'm going as fast as I can in the x velocity, in the x direction. That's the trick, is like you got to get fast people for long jump. But the horizontal speed alone isn't good enough. Because if you have this y velocity, I drew a ball, but if the jumper has that y velocity versus this y velocity, what's the difference in the jump? Keeping in mind that the x is going to be constant, what's the difference between y velocity number 1 and y velocity number 2? What is the difference, and why does it make a difference? It's exactly right, because the y velocity has everything to do with how much time you are in the air. So this y velocity will give this x velocity more time to act before you touch the sand. So if I'm going with this one, that first one, my jump will probably be something like this. But if I was going to go, keeping in mind my x velocity is the same the whole time. If I go with number 2, y velocity, x velocity the same, it's going to look more like this. And notice it's higher. And you ask why? Well, the reason is why. The y velocity gets you higher, more time in the air, so more time to make that state record jump. Okay, so our next little bit of notes here is something that we've been talking about quite a bit. But it's so important, I don't want you to forget. So I put it on again and again and again. It says any projectile will fall at a rate of 10 meters per second squared, assuming that there's no air resistance. So it doesn't matter if it's a ball, a feather, a leaf, a marble, a football, it doesn't matter. They all fall at the same rate. And that was one thing that they used to think was wrong. Like, on the Leaning Tower of Pisa, a famous scientist dropped some big rocks and little rocks. And the question was, the thought of the day was that, hey, this big rock, it's heavier, so it's going to fall faster. But what did they find out? They found out that the big rock and the small rock fell at the same rate. And so that's where they came up with this idea, or started to come up with this idea that, hey, the force of gravity accelerates things at the same rate no matter how big it is. Okay, so don't forget that. 10 meters per second, no matter what it is, as long as there's no air resistance. Okay, and just to reiterate again, this note says a projectile shot upward or downward will accelerate at 10 meters per second towards the center of the Earth. So if I'm shooting this projectile up, it slows down because the acceleration due to gravity is in the opposite direction of the initial velocity, so it slows it down. And then on the way back down, though, it goes faster and faster and faster, because on the way down, the velocity is in the same direction as little g. And so if acceleration and velocity are in the same direction, it speeds up. If they're opposite, it slows down. No matter where the projectile is at, it will always be accelerating at a rate of 10 meters per second squared downward. So you better put that in your notes that that's downward. I should have had that in PowerPoint. I don't. Okay. So this piece we already talked about the athlete that jumps faster or slower horizontally. Or no, we didn't talk about it. Will have the same hang time if the vertical velocity is the same. So what that means is, if I have a ball that moves like this, same ball moving like this, so if the initial, okay, so the initial y velocity on this one is that big. Would this one be bigger or smaller? Bigger, yep. And how do you know that? Because it goes higher. So the larger the velocity in the y direction, the higher it will go. Now, this says the athlete jumps faster or slower horizontally. So this is the horizontal. So really, and I think I'm fumbling around here with trying to explain this to you, but what this is trying to say is, like the bullet in the gun. So remember we had that video, Mythbusters, y'all watched that? And the bullet was shot out of the gun at a very high velocity, and at the same time another bullet is dropped from the same height. So I probably should have drawn that somewhere else. I guess it was like this. It was dropped, and this one was shot out the same time that was dropped, and they landed in the same place, or at the same time. They landed at the same time. You watched the Mythbusters video, right? So this is just to remind you that it doesn't matter about the velocity in the x direction. The velocity in the y direction is the only one that is affected by gravity. And bullets are good because they're like symmetrical all the way around. There's no lift. Now, if you shot an airplane, that would be a different story, right? Because airplanes are designed to fly and keep afloat longer. Okay, so this is really all about independence again. So these velocities are independent of each other. Okay. Okay, so here's another thing that we've already talked about. It's all about symmetrical or symmetry. So remember when we said that things going up and coming back down? We said that going up is symmetrical to going down. So if I have a velocity in the beginning, it's going to be the same number velocity in the end. It'll be a different direction because this one is in that direction, this one is this direction. But if I shoot it up at 10 meters per second, it's going to be 10 meters per second on the way back down at the same spot. If I take a piece here, and my velocity is 5 at this piece, or at this point, on the same horizontal plane, it's still going to be 5 meters per second, but in a different direction. So this whole thing, idea of symmetry is like, you cut your throw or your kick or your shot in half, and everything on this side is like perfectly symmetrical to everything on this side, in the absence of air resistance. Okay, so just one more kind of explanation here. So let's say I take a ball and it's 5 meters per second. It's gonna like hit the ground. Let's say that it takes, well, it's 5 meters high to the ground, and I know that in the first second that something falls, it goes 5 meters down. That's something you might want to memorize. But so if it took 1 second, that means I went 5 meters here, right? That takes 1 second to hit the ground. And why is that? It's because it's 5 meters above. Let's just say that I take another ball, like a different color, like a blue ball, and I shoot it at 10 meters per second. How long is it going to take to fall down to the ground? Yeah, exactly right. So I know he said, first of all, he said 2 seconds, but then he doubled back because it's still only falling 5 meters, and the whole x velocity and y velocity are independent of each other, which means it doesn't matter how fast I'm going this way. I still start with a y velocity of 0 and end up, you know, in the same place in the y direction at the same time. So this still only takes 1 second, which is one of those things kids never get when they first come into physics. Now, but what is the difference? Well, the difference is it's still the same time to fall, but it's going twice as fast. So the overall distance it covers is twice as much. Okay, so let's just say that we're looking at a skateboarder. Anyone skateboarding here? Okay, is there ever a trick that you do? So let's just say that one of your tricks, and I don't know what the tricks are, includes you jumping up. Oh, they do? Okay, they all do. Okay, so you're jumping up as high as you can, right? And so let's just say that you can jump up 1 meter, which is like 3 feet. That's pretty good, right? It's 3 1/3 foot or 4 feet. Okay, so let's say that, you know, you're going 5 meters per second and you're able to jump up 1 meter, right? What happens if you're able to go, like, instead of going 5, you're going 10 meters per second? And you, again, jump as high as you can. So you use the same amount of muscle and stuff like that. How high do you go? Do you go lower, higher, the same? What's your answer? Very good. Yeah, good. You got it right. You go the same. It's only 1 meter. That's as high as you can jump. It doesn't matter how fast you're going. And that's the whole idea of the horizontal and vertical being completely independent of each other. Okay, very good. Okay, so back to like some ideas of, or I don't know about back to, but look at this note. It says a ball kicked at 45 degrees will have the greatest horizontal range. So if you're kicking at 45 degrees from the horizontal, then what that means is your x velocity and y velocity are the same number, right? Because if it's 45 there, it'd be 45 here. This is a 90. And so these two legs of the triangle are the same. It just so happens that 45 degrees is that magic number where you get the longest range out of a kick. So anything more or less than 45 is going to be, so like let's say it's 50. If it's 50, it's going to be less than that. If it's 40, it's going to be less distance than that. It'll be a little higher though. Okay, so 45 is the magic number. Remember that. Here's something interesting. It says the ball kicked at 75 or 15 will have the same horizontal range. So if I'm kicking a ball at 75, it's going to look like this. Okay. 15 is going to look like this. So see, what's the difference here? The one at 15 has more x velocity, less y velocity. That would be this one. And then the one at 45 here, or I mean 75. So 75 is pretty drastic. It'll have smaller x velocity and a higher y velocity. Which one's going to be longer in the air, Evan? The 75 or the 15? Yeah, that's exactly right. So this y velocity here is much bigger, so it's going to go a lot higher. So there's more time in the air. Where this y velocity is smaller, there's less time in the air. So does that make sense that, hey, this one has a faster x velocity, so it needs less time to get to the same spot as this one, has a a much smaller x velocity, but it has that much more time because it has much higher y velocity. What do you notice about these two numbers? 75 plus 15 equals what? 90, right? And that's kind of the magic number here. So degrees that add up to 90 will have the same horizontal range. So 60 and 30 will have the same horizontal range. 20 and 70, 10 and 80 will have the same horizontal range. So that's something you're going to want to put together as a pattern. Okay, so this says for very long-range projectiles, the curvature of the Earth must be taken into account. So here's the deal. On top of a mountain, you got a cannon, and you shoot the cannon, and it hits the ground, right? And here's the Earth, right? Shoot the cannon a little bit further, it hits the ground further on down the line. You shoot the cannon fast enough, and notice now, as this projectile, let me draw a little bit better picture. Okay, so here's the Earth, and here's your mountain, your cannonball. So you shoot it, it goes kind of far. You shoot it faster, it's going to go further, right? Shoot it faster. If you shoot it fast enough, look at that. See how, it still has this projectile path here, but it's shot fast enough in the x velocity that every time it falls according to the y velocity, because the force of gravity is pulling it down, the Earth is actually moving away from it at the same rate. So keep this in mind. In 1 second, if I drop a ball, in 1 second, if this initial velocity is 0, it drops 5 meters. So if you want to have a satellite, which is something that continues to orbit around the Earth, then you have to match those two things. So right here it says the distance that a free-falling object falls is 5 meters in the first second. So that last picture I drew was all about this. If a projectile is launched fast enough, the curvature of the Earth can come into play. And if you launch it just fast enough, here's the Earth. If you launch it too fast, then you're headed to the moon, Mars, and beyond. If you launch it too slow, you crash into the Earth. If you launch it just right, and I'll tell you that magic number on the next slide, then the curvature of the projectile motion matches the curvature of the Earth, and then you're in orbit, which is what satellites are. So like the International Space Station is orbit. And here's the magic number, 8 kilometers per second. So if you're on the Earth and you go 8,000 meters in 1 second, that's perfect because the curvature of the Earth itself falls away 5 meters for every 8,000 meters in the horizontal. So that if you want to get orbited into space, you got to go 8 kilometers per second or 18,000 miles an hour. If you go faster than that, you're out of this world. If you go slower than that, you smacked into the world. Okay, interesting note. Have you guys ever seen a falling star, they call them? You ever seen a falling star? You've never seen one? A streak. Yeah, it's exactly what it is. So when the meteor is flying through space, when it hits our atmosphere, it melts and burns up. And that's the bright light that you see when you see a falling star. Here's another little bit here. Satellites orbit above 150 kilometers, where the air resistance is almost nothing. An average orbit is somewhere between Fargo, from here to Fargo and St. Cloud. So 200 and 250 miles above us is how far the space station is on average. Okay, do you guys have any questions? Okay, hopefully this helps you with your test or your quiz. Have a great day.